second seminar in this general line of looking at dilute plasmas, and this is Matt Kunz, and he will talk about that.
This. Right. Thank you. Excuse me for coughing and all sorts of other things.
You can cough, but the other things.
The other things I might have to hold off on, so not too many questions or else I'll run out of time to do other things. Right, so some of this stuff is work that I'm doing right now with Alex. Early on the talk, I'm going to plagiarize heavily from Steve, but I guess it's not plagiarism if I put his name there, so that's what that is for. I'm also going to discuss some things that Jim Stone is doing at Princeton with some simulations, and we'll get to all these things, and hopefully everyone will be happy with the credit they get. Right, so just to review from this morning, but in a different context, I'm working in this regime that Steve referred to as the dilute plasma limit. It's a weakly collisional limit where there aren't many collisions, but all the sort of time scales and length scales that have to do with the viscosity and the collisions and the Larmor frequencies, these are all still, there's a good scale separation between that and the large scale quantities, like if you're in a disk, the rotation frequency of the disk or the scale height of the disk h. So where would this sort of plasma limit be applicable? Well, other than the interstellar medium and galaxy clusters, like Steve discussed, there's also accretion disks of a certain type. Protogalactic disks, radiatively inefficient accretion flows. That's the prototype for that is the accretion flow onto Sag star at our galactic center. I've got a little caveat here about the electron temperature, which is debatable at the moment. But these are hot and diffuse systems, and they satisfy this type of ordering. So these are the types of systems I'm thinking about.
Wait.
Yeah.
Really true in an RIAF, lambda mean free path over H is much less than 1. My understanding was that a lambda mean free path over R was order 1.
Yeah, it's right. So there are regions where that's true, and there's.
What's H?
This the scale height of the disk.
This is not a thin disk. H and R aren't very different.
Yeah, but I'm saying lambda mean free path was order R, not much less than.
Or even with
Yeah.
bigger.
Or even bigger.
Yeah. Yeah. So.
You can't say anything.
Right. So in these systems, right, you have to be. If you want to do a proper job in these systems, you should do a kinetic calculation. This has been done. Greg Hamett's here. He could talk all about it. I'm not going to really talk about these systems much. I just put them up here as an example.
So just to say, I understand why you call it weakly collisional, but there's a really broad range of plasmas for which that left criterion, omega ci tau I, is much bigger than 1. It doesn't take. You can still have short mean free path in many systems and still satisfy that because the cyclone pulse is so rapid.
Right.
Except in the sun. The sun is so dense and the magnetic field is so weak.
So some strong.
Okay. Right. So being new to this sort of game, what's at my disposal as a newbie are the Brzezinski MHD equations. Here they are. And these should be familiar to most everybody in this room. So what I'm going to do first is introduce instability that Steve found. And I'm going to discuss some properties of this.
Couldn't put a pressure equation on the previous one.
Won't need one. Yeah.
You won't need what?
A pressure equation. One of the components of the Monod equation determines the pressure. So it's,
Why is
So I'll work within a Boussinesq approximation where, you filter out your sound waves.
Assume that everything's happening slowly compared to the sound speed.
Right. Okay, so you set up a disk in some sort of rotation, like Keplerian rotation, and you've got a balance between the gravitational potential and the centrifugal force. Go to some local patch in the disk, and you linearize things around the local patch. So there's a shear from the background velocity gradient, angular velocity gradient, and we're going to take the field to be as general as you can without complicating things. So that would just be a phi component and a z component, and do the usual linearization process. I'm going to work with a real frequency for that'll be a growth rate instead of a mode frequency. So we'll just look at the dispersion, the relation that emerges one step at a time. If you do away with the field and all the Brzezinski viscosity and everything, you just get a rotational instability. So there's the epicyclic frequency, and you get a rotational instability, the usual Rayleigh criterion. This is not satisfied in accretion disks. For future reference at the bottom, I'm computing this is a radial angular momentum flux. So because the kappa is actually positive in accretion disks, you actually transport angular momentum the wrong way. Steve talked about in the first week about the MRI, what happens when you add a weak seed field to the problem, and it changes radically. You no longer are concerned with things like angular momentum, you're concerned with things like angular velocity. And so instead of a kappa for the epicyclic frequency, you've got this that angular velocity gradient instead. And so this needs to be negative for instability, and this is easily satisfied in a wide range of systems. And then I just, so you can see the difference. Here's the angular momentum flux again. If you didn't have the field, this would just be gone, and you get that minus kappa squared from the rotational instability. And this ensures that there's actual outward angular momentum transport. What do you want to say?
That second equality in the flux is a quasi-linear estimate, or I mean.
Yeah.
Okay.
Yeah. Right. So you keep going, and you want to do you want to look at the weakly collisional regime, and this was actually explored with two different approaches. One was a kinetic approach, Elliot Quadert and Greg Hammond and Pratik Sharma and their collaborators, and then one other approach that I think distilled the physics a little more for me was the fluid approach, because I wasn't aware of kinetic things when I was younger. And so
Now you're older and wiser.
yeah.
No, they're just, you have to be at least.
No, now I'm just older. You have to at least be. All right. So you get a messier dispersion relation, but you can basically see what's going on. There's a point. So up top, this is just the MRI dispersion relation if you get rid of everything else. Here's collisionality that comes in because of the pressure anisotropy, and you have this extra term. I'm keeping things formal right now mathematically, but we'll revisit physically what's going on in a second. So for the MVI, you still have the same criterion where the angular frequency, angular velocity decreases outward. And if you go and you compute the angular momentum flux in the same way, but just forget about the Maxwell stress, so you filter out the MRI, you get something similar where instead of k squared VA for the alphane frequency, you get a k squared V thermal squared And you can see that you really need this, within these vertical perturbations at least, you need or vertical wave numbers at least, you need a azimuthal component of the field. So the talk is mainly going to focus on variations, inversions, and evolutions of this guy. So let's see what this actually looks like.
Little b here is a unit vector.
Yeah, I'm using the same notation that Steve did this morning. Oh yeah, sorry. Right. Yeah, it's the. Okay, so you can. This is a bit cumbersome because you've got the MRI here, and because of the Viscous stress, it's coupled to this MPI branch. So you can go to a certain limit.
I got confused by Greg's question. What is little b?
Little b is a unit field vector. So b phi would be the portion of the unit magnetic field pointing in the phi direction in the disk.
Why do you square that? I don't know what's going on with
I'm sorry, why do I square it? Or
that. You've got it, I just don't understand what it means. Have that squared?
it's
Unit vector?
it's the component.
Component of a unit vector.
Yeah.
Functional on the magnetic field.
It's cosine.
Cosine squared. So
Okay. Little b doesn't
So
You'll see why it's necessary in a second. Yeah.
I think in your previous slide or two you had the magnetic field. Did you define little b?
No, I didn't.
It's just the angle. It's just the cosine of the angle between the magnetic field and the azimuth.
Yeah.
Right. I should go a little slower. Yeah. Or a lot slower. Okay.
what confuses me actually, Matt, is that gamma could be purely imaginary. I don't know what it's doing in an angular
Where do you see this? Where?
Should let you go on.
Okay.
Gamma can be imaginary,
Yeah. No, I'm just a little confused by the expression.
but in that case it's stable. But if you have if it's unstable, then gamma will be real.
Yeah, but in the angular momentum flux, it should come out with a real answer.
Yeah. No, you take the
So
take the real part of this. Okay.
I suspect it's delta VR times delta V phi
Star. Yeah.
you know, et cetera, et cetera.
Now each of the deltas should have a real in front of it.
Right. Yeah. I was just.
Before you multiply together, you
I'm
take.
sloppy here, but yeah. This is right. Right, so just to distill things a little further, because it's a little cumbersome, you can separate out this NVI branch from the MRI. So you can take basically kill off all the Lorentz forces, or you could take the wavelengths to be extremely small. And you get this maximum growth rate, which all four of those papers that I mentioned found. The reason why I put all this math here before we got to the actual physics of what's going on is I just wanted to point out one mode, or one interesting part of the math that will motivate the rest of the talk. There's this gamma equals 0 mode, which is just sort of sitting there. And it would be nice to know if that gets activated if you do anything different in the analysis. Okay. So just to look at the growth rate of this MVI, this is growth rate. This is KZ times the scale height. And this is in the limit where you just throw away all the Lorentz forces and all you're caring about is just viscous transport or pressure isotropies, the same sorts of things. So when the collision frequency is really weak, you just come up here to this maximum growth rate, and as you increase the collision frequency, you just asymptote slower and slower to this maximum growth rate. If you were to add, you can see there's a bit of a problem, of course, with Viscous gamma HD. If you keep on going to higher K, eventually you'll hit there needs to be some sort of dissipation at the high K. and that's not in the Brzezinski calculation. If you add a magnetic field so that instead of the thermal pressure scale height, you plot a magnetic pressure scale height, the magnetic field truncates the growth rate because it has a tension. There's an MHD limit, and as you decrease the frequency, the growth rate keeps increasing until it asymptotes to the same value right there. Right, so what does this look like? So the rest of the talk will dispense with a lot of the math and just focus on physical processes. So if you have a disk where you have angular velocity decreasing outwards, like most astrophysical disks, and you've got fast and slow, and this is a chain of events, so you have some field lines that look like this, and you've got two fluid elements, and you put a perturbation in the field lines. There's two different ways of thinking about this process. One within the Brzezinski framework is that you generate viscous stresses, these transport angular momentum, and as you stretch the field lines, you get more and more of this viscous stress oriented along the angular frequency gradient, so you can keep on stretching. Another way to think about it from the kinetic point of view is that these modes are basically slow mode perturbations, and when you put a slow mode perturbation into a weakly collisional system, you generate a pressure anisotropy. That pressure anisotropy acts like a viscous torque, and you get the same sort of runaway. The key point is that angular momentum is channeled along field lines. So just like this morning when heat flow was channeled along field lines, here the angular momentum is channeled along the field lines. And on the verge of instability, you have the Lagrangian change in the fluid element's angular velocity is 0 when you put in a trivial displacement. So that's the real key. You're embedding fast guys in slow orbits, and you get angular momentum transport along the field lines. So one thing I wanted to point out, we shouldn't be here, is here's this MVI. If you turn the diagram sideways, you get one thing that Steve talked about this morning is the MTI, thermal instability. So instead of fast and slow, you got hot and cold if you're in a stratified atmosphere. I won't review that. He also talked about this heat flux buoyancy instability, where instead of hot and cold, you have cold and hot. And instead of these types of perturbations, you put in perturbations where you get converging field lines, so that the heat flux converges in places and it diverges in other places. So there seems to be some sort of asymmetry here. There's a disk version and a stratified atmosphere version that have to do with similar perturbations, but there's no rotational analog to this HBI that's been found yet. So that's the first part of the talk. We're going to explore this question mark. All right, so by analogy with the HBI, suppose that there's an angular momentum flux in the background state, because for the HBI you needed a background heat flux. So the only way that you could do that is if you have a BR and a B phi, and they couple to the shear, and you generate a pressure anisotropy. Then, if you want to write down the perturbed pressure anisotropy, you get several contributions here. You get one that's from the fluctuations, one that's from the shear acting on that radial field that you generated. Both these terms are in the MVI calculation, but then you have this other term here. And this is due to azimuthal perturbations being put on top of this background pressure anisotropy. And we're going to explore this last term. So you can clean things up. And it turns out that I'll show this extra term here is related to that gamma equals 0 node in the MVI calculation. Yeah.
So you're envisaging your disks being weakly collisional, what's the pressure relaxation time? What isotropization time of this plasma?
So
Is that
the
sufficiently long that you can actually have a pressure anisotropy in the background?
yeah, but you only need a very weak pressure anisotropy. Yeah. Yeah. So this is of order omega over nu, which is a small number necessarily in Brzezinski. But that'll be enough. You just have to go to high K. Compensates for the difference.
This is a case where you're tilting the field lines due to them being wrapped up. Is that right?
Rather than them being spooled on cylinders, yeah. So if you put a little radial tilt into it,
Yeah. And the differential rotation is now wrapping the field lines up.
right,
So the field strength is rising.
right,
That's driving a P part bigger than a P barrel.
exactly,
There's a mu conservation.
yeah.
Little,
I'm not
is it
sure.
the wrapping of the field line or just the fact that you have VR, which is tapping into a background source of momentum, just Coulomb collisions? Coulomb collisions along the field line.
Yeah, I think these are different
Wrapping
ways.
is going on, but I don't know that that is the reason for.
It's the same.
It's the same thing. It's different ways of thinking. I mean, you're thinking viscously and they're thinking kinetically. It's
No. It's the same thing because d omega by dr over nu is the pressure anisotropy, and the pressure anisotropy is d by dt of the magnetic field strength.
Well, I guess the way that Steve described it, it seemed like somehow the time dependence of V5 was key.
Time dependence of the total magnetic field strength.
Yeah.
The field strength, not of the
We
field.
can write the term. It's because kinetically what's happening is you're changing the magnitude of B, which means that V plus squared has to go up to keep mu constant.
So the right-hand side of the equation on top can be written as little br little d phi times d log d by dt. Yeah.
Right. So you're thinking in terms of stresses in the background. It's the same.
Well, I think if you divided the left-hand side by
Oh,
P
I knew it would be even better.
and the right-hand side, yeah, and well also the middle. Let's divide it by
1 over nu.
1 over nu.
Yeah.
That's right.
Right. Squiggles were meant to take care of all those sorts of things.
Yep.
Okay. Yeah.
I'll ask another question. Can you construct an equilibrium with this sort of magnet with all the components in,
You'd
and
be
then
hard
anisotropic
pressed.
pressure, and gravity and inertia?
I doubt it. Yeah. So
Okay.
this is right. This is a time dependent background, and so what I'm about to do is very sketchy, but I didn't want to go into the details for this talk. Right. And the talk will be there'll be some weekly rigorous math to justify a qualitative picture that I can guarantee is right from more rigorous math that I won't show you.
Dilute rigor.
Right. I'm diluting the rigor just for this audience. No. Just for me so I can explain it. Okay. So this is the idea. So Steve talked this morning about how if you have a heat flux that follows the field lines, you can pinch the field lines and locally heat fluid elements. If you have a background angular momentum flux that we've created, you could do the same sort of perturbation, and where you're locally converging the field lines and also locally diverging the field lines in other places. And by analogy, the angular momentum follows these field lines, and when you pinch it, you're going to locally spin those fluid elements up. So the Lagrangian change of omega in those cases would be 0. And it turns out that for a trailing configuration, so BR and B phi would be negative. If you perturb this fluid element inwards, it actually accumulates angular velocity and, sorry, these are backwards. If you perturb the fluid element outwards, it's going to accumulate angular velocity and continue moving outwards, right? The other way too. These are backwards. So you end up with this angular momentum flux, viscously driven instability, just like the heat flux, buoyancy driven instability. It's the same sort of process. So that gamma equals 0 mode actually becomes unstable, proportional to the shearing rate. There's a geometrical factor that has to do with the wave vector orientation, whether it's parallel or perpendicular to the field, because you need to generate slow mode compressions. And this is just some number that has to do with the field orientation. Right. Okay. So is there any questions about that? Because I'm going to move on to something related but different.
It's always unstable no matter the sign of rotation.
Yeah, you can find some modes that are always unstable. Right. Yeah. This is it's sort of like a mirror instability, but it's different because in a mirror instability, you're taking a pressure isotropy, you put slow mode perturbations in, and those grow. But this is in the fluid regime where you've got a background pressure isotropy, which is equivalent to angular momentum flux. You're pinching that, but instead of having resonant particles and all this stuff, all you're doing is converging the angular momentum flux in places, and so you can locally spin up those elements, and you take free energy out of the pressure isotropy, put it into rotational energy for a fluid element.
So it's a type of mirror that's a balance of inertia and pressure anisotropy, not resonant particles.
Right. Okay.
Very touch and go.
No, yeah.
The problem is that the growth rate is directly proportional to the shear. It's also proportional to the order of terms that you're dropping.
No, yeah. This is schematic, just to present a picture.
It's okay.
Yeah, I'm not claiming it's.
Long, that's not okay.
No, I'm not claiming it's rigorous. I did the rigorous calculation, but it's.
So what's
Yeah, it's this with a different number out front, but it's still the same. Okay.
I
Just wanted to present the physical process that you should expect physically to happen.
mean, you've got, this should happen in a sheared slab. Right? We don't need Keplerian orbitals.
No,
right?
you do. Okay, so it's a little subtle, right? So
Gravity.
if you're, it looks like a mirror mode, which you can have in a slab, right? But it's actually, it's a little different, and it really has to do with transferring angular momentum from one fluid, well, from the background into fluid elements. You can
The sort of notion of angular momentum buoyancy is part of the instability that require angular momentum rise. That's something which is a rotational concept.
Yeah, but that's the interpretation. But mathematically, you're going to get the exact same thing.
That's why I'm worried about the form of this growth rate.
If you do this calculation on a slab, you'll get, well, if you do this sketch that you showed, you will get the exact same answer with R now X, Phi, Y,
Yes.
and so on, right?
It's
But the interpretation for it will be different,
it's
right? Or maybe it's not even that.
it's yeah, I wish I just wrote up the rigorous thing on here and made it a mess. But you get a different answer. It's the same sort of thing. I mean, you have to get a growth rate that's proportional to the shear, because ultimately that's the free energy source, whether you're in a slab or whether you're in a disk. But
If you just do this analysis in a slab,
yes,
is there an instability?
well, it's just a fluid version of a mirror.
Right.
Yeah. But a fluid version of a mirror, if you go computing Lagrangian changes in velocities and stuff like this, you'll get different answers than here, because this really has to do with there's terms in here that have to do with extracting rotational energy from the background.
Matt doesn't look like a mirror to me because this is the growth rate, right? The growth rate doesn't rise with K.
Yeah, so neither does the mirror.
It would rise with K if you had the mirror, which is a balance between the resonant term
Yeah,
and the
so
anisotropy. That you don't have that in the.
so in the fluid mirror, it's
It's
something like
omega
this.
squared equals to 1 over beta kind of thing.
Okay. So something less controversial. All right, go back to the MVI, and we can ask a question: how is this going to evolve? And the first thing that you should compute when you ask how it's going to evolve is the box averaged, if you were simulating this, the box average or system average pressure isotropy. And there's two terms. There's one that's generated by the background shear, and there's one that's generated by the fluctuations. And you can compute this for the fastest growing modes, and this is what you get. You get a positive pressure isotropy if you go averaging over all the modes in the box. It turns out you need a positive pressure isotropy to transport angular momentum, so this all makes sense. There's been collisionless MRI simulations for Pratik thesis, and you see the same sort of thing where you generate a positive pressure isotropy if you integrate over the box, and you get angular momentum transport. So you can ask the question, what does this imply about the evolution? The problem is the MRI that was reviewed during the first week, there's versions of it that are exact nonlinear solutions. The MVI is not, because you're generating pressure isotropy. Pressure isotropy has all these higher order terms. And as it goes into the nonlinear regime, these terms get more and more important. One thing that happens is that the pressure isotropy source stiffens the plasma. It acts like an effective magnetic tension, and it's an effective magnetic tension that's exponentially growing. So your plasma is getting stiffer and stiffer, and ultimately it wants to shut itself off. But then what happens? So you can look at the viscous stress tensor, and you can figure out what's going to happen. If you look at the first term, this has to do with generating a pressure isotropy along some sort of background magnetic field. You get a slow mode perturbation. Viscous stress is angular momentum transport. This is just the MVI. The second term, you can show results in a modification of the Alfvén speed. So the plasma gets stiffer, and the MVI modes tend to stabilize themselves. You can show this explicitly by, this is growth rate of the MVI versus Kz times the scale height. If there's no background pressure isotropy, you get what we just had before, where the high K modes just asymptote to what's effectively the shearing rate. And as you increase the pressure isotropy, the higher K modes get stabilized because it acts like a magnetic tension, and you also weaken the growth rate. If you look at the third term, this is basically what results in the fluid version of the mirror instability, and this is why I presented the other thing first. You're generating a pressure isotropy. The fluid can tap into that pressure isotropy, whether it be kinetically or Baginski or whatever. And this is why I'm a little flaky on the math right now, is I just want to sketch out this qualitative picture. The MVI generates a pressure isotropy, stiffens the plasma, but it's also a free energy source. And so if you allow mirror modes to exist, they can take energy out of that pressure isotropy reduce the tension. This has been seen in simulations that Pratik did. What hadn't been seen, and what I'm going to talk about now, is conjecturing that some balance ought to be achieved between the MVI growth and the mirror modes. So the MVI pumps the pressure anisotropy, and the mirror modes deplete the pressure anisotropy, and they should come into some sort of steady state.
Sorry, but, I mean, I don't think this was seen in the simulation. This was implemented in the simulation. So it's the fact that the mirror depletes the anisotropy was not an outcome of the simulation.
Right.
I mean, there was some term there.
Yeah, I didn't say it was in. I didn't say this part was in the simulations.
No, you said this was seen in the simulation.
The
So the fact that the mirror depletes the pressure anisotropy.
okay, I meant the tension part, the stabilization of the modes, and then you right, and then you artificially decrease the pressure anisotropy, and you let it keep evolving. So if you just do a fluid calculation, which is technically incorrect, but it's illustrative. If you put this term in, you'll have the MVI here.
What's that?
Alpha is just a measure of the pressure anisotropy in funky units. Don't worry about it. The idea is that as you turn the pressure anisotropy up, it's basically nu times the pressure anisotropy. As you turn it up, just like before, the long K or the high K modes get stabilized because it acts like a tension. The growth rate decreases, but as the pressure anisotropy gets large enough, you trigger these sorts of mirror modes in the plasma. And right, so this is just a schematic.
Is this the only growth rate? Is all the other modes
The other
are negative?
Right, yeah, the other modes are damped or wave-like. All right, so I'll conjecture that what you should ultimately find yourself in a situation of where the MVI growth keeps getting lower, and if you're increasing the pressure anisotropy, the mirror growth rate will go up, and then you'll find a situation where this guy can't grow anymore because he'll deplete it faster than the MVI can supply the pressure anisotropy. He can't grow anymore because the pressure anisotropy is too stiff to let him keep on going. So I'll sketch that out in words.
So I'm puzzled. I thought the mirror growth rate increases with day when you have it in flat.
Yeah, so what I had in mind is it's not saying. Is this yeah, it's fluid version like what I sketched out earlier where you rotationally tap into the pressure anisotropy.
If you had a resonance in the system, then mirror growth rate is the balance between the resonant term and the anisotropy term. The resonant term has a gamma times k perp squared over k parallel, and that has to be equal to something constant. So gamma has to be like proportional to k parallel. If you don't have that resonant term, then the dispersion relation looks like omega squared minus pressure. So it's a fluid mirror, it's not the same instability. In the kinetic, if you were kinetic, if you didn't suppress those resonant terms, there would be a term that's bigger than the one. It's exactly like you get the same instability condition, right? It's exactly the same reason why CGL gets mirror, even though it doesn't have resonance. So you get an instability, but it's not quite the same instability.
So there are in fact high K mirror modes that are beyond the description you're using.
Yes.
Have even higher growth rates than the one you're talking
Yeah.
about. And I think that those modes are going to grow and saturate first.
Okay.
But
Yeah, it's hard to say at this point. I don't know. Actually, get to that. Yeah. Okay. So this pressure anisotropy generated, viscous torques transferring momentum outwards. MBI ensues, you grow a magnetic field strength. Because you're growing it, you produce a pressure isotropy that ultimately stabilizes the MBI. And MBI wants to saturate with some positive stress and positive pressure isotropy. But you have secondary instabilities, whether they're fluid or kinetic, we'll talk about in a second. They tap into that. You get a balance between something that's sapping out the pressure anisotropy and something that's generating the pressure anisotropy. And the field strength should keep going until the tension becomes important. So visually, this is what I envision. So there's radius and azimuth. Here's some field lines. You put an MVI perturbation into it, and those arrows are angular momentum that's channeled from one fluid element to another. And then if you go putting slow-mo perturbations along those field lines, you could tap into that angular momentum flux. So just like at the beginning where you pinch the field lines, you're converging the angular momentum flux in areas and you're diverging it in other areas. And so can we capture this with a reduced model? The problem is that you can't actually, I've tried really hard, you can't write down a nonlinear set of equations for this and solve them. But you can do two things. You can try to approach it simplistically with a reduced model analytically, or you can do it with a simulation. And that's where Jim Stone comes in, and I'll get to his results.
Sorry, just before you.
Yeah.
You said that so your neural-like instabilities have IK cutoff.
Yeah.
Right? But zero, I mean, you have a perturbation of the Braginski tensor as well.
Yeah.
Don't you have a cutoff, a bit like a viscous cutoff? Because these are not polarized.
It has a cutoff at low beta. So what I showed you was for infinite beta. There's a tension cutoff for that too.
Not about tension, I mean
Oh.
regular viscosity. Because you have a B dot
Yeah,
dot
good
U C.
question.
And if U is not polarized like a Eigenwave, then you should dissipate. I mean,
He has that parallel viscosity against it. But
Yes.
it's driving instability.
well, there are two terms there, right? Because there are
Yeah.
delta B's, dot red U,
So it's a
and
new,
BB dot
it's
red
a
delta
new,
U.
it's a new k parallel squared.
Yes.
Yeah, there should be a minus mu k parallel squared u parallel.
Yes, something like that.
Is that got anything to do?
I'm trying to visualize this term. So there's two types of terms. There's ones that generate pressure anisotropy and there's ones that exploit pressure anisotropy.
No, but there are also ones that just viscously damp things.
Oh, I see. So like, yeah, k squared
Yes.
times a diffusivity.
So if you have these terms, I would think that the growth rate is going to decrease, right?
No.
They might balance with. I can't.
No. These terms aren't.
Oh yeah, k parallel must cancel there, right? Because you have some parallel.
There's not a k squared times a diffusivity. There is.
No, there is a term like.
Yeah,
this.
it's a term like that,
Must
but
be balancing with something else.
it goes into it's part of the pressure.
What?
It's part of the total pressure. So there's
No.
yeah, it's where's the, I keep
Generally, there isn't a term that wins at IK because they're all scaling like k squared. It's analogous to the MPO.
Yeah, that's what
Even-
Francois is asking.
Yes, so that's the same thing as for the
The same question.
I think that's right.
Yes. In the delta B, it's
The same
The
question.
delta B has a k dependency,
Alright.
which is not
It's exactly the same story.
yeah, right. It's the same story as the
Right. So what's the answer?
The answer is I think that term is there, but it does not ultimately win at IK.
yeah.
It has competition.
Yeah, because there's a k parallel hiding somewhere.
That's right.
Okay.
So not dissipating, I mean, Braginski not dissipating these things. It's not just an
Yeah,
issue with
yeah, yeah.
Eigenwave.
It's because It's because delta p perp minus delta p parallel has a k parallel already somewhere, right?
Yeah.
That's right.
So
Yeah.
the problem with Braginski is not only with Eigenwave not being dissipating, it's all sorts of modes not being dissipated.
Yeah, Braginski dissipation is.
Well,
It does ultimately dissipate nonlinear.
Yeah, right. This is a pressure anisotropy square term in the energy equation, but it's a nonlinear term.
No, it does dissipate stuff, but
Yeah.
it's not true that any linear mode you throw at it will be dissipated, right?
That's right.
None of them seems to.
Dissipates stuff. but
None of them. Well, actually, I think that the fact that he had his MVI dropping and then mirrors starting
Mm-hmm.
must have something to do with it. No, maybe.
They're on the
but
same
it's
branch. They're
talking
both
about,
on the slow-mo branch. It's-
no, but where that place is not by any chance regulated by that place where MVI
No.
drops mirror.
It's regulated by when the effective tension becomes comparable to the shearing rate. Yeah. Okay. So this sort of evolutionary scenario, can you capture this with some sort of analytic model? So what I'm going to do is I'm going to call the MVI our primary, and I'm taking a page out of the Le Safra about this ladder book. And there's a primary mode. This is like a turbulent fluctuation. It grows with a growth rate that depends on the pressure isotropy that we just showed. And this is sort of like a saturation term that I took from their playbook. And this is just an analytic fit to if you plot the growth rate as a function of pressure isotropy times the collision frequency, it goes like this. So of course it needs to go to 0 in the collisional regime, and it's at its maximum in the collisionless regime, and it's smooth in between. You make some equation to model the secondaries, which would be this mirror instability. This is just a parameter that has to do with the orientation of the wave number. It's a free parameter. So there's a growth rate that has to do with the pressure isotropy because it's feeding off of the pressure isotropy. And there's a stabilization that happens because of high beta. And then you need an equation that governs the pressure isotropy. The MVI generates it, and the secondary mirrors deplete it. And you can solve these pretty easily on the computer. Yeah, that's what I just did.
I'm a little confused. The combination nu times delta appears.
Yeah,
So the drive goes away at high collisionality or high pressure anisotropy.
right.
Why does it go away at high delta?
Because it acts like a tension, which tends to stabilize these modes. This is what it would look like if you didn't have anything to break that tension. Right? It would just stabilize. So you solve it and you plot magnetic energy versus orbit, and the details are debatable because it all has to do with these free parameters that you always get in these reduced models, but you generically always find something like this. You have this rapid MVI growth phase. There's a temporary stall here, and that happens when the tension becomes strong enough to compete with the shear that's trying to stretch the field lines. But what happens is these secondaries feed off of the pressure isotropy and weaken it, and you get into this balance, and you get this secondary growth phase, and ultimately, once the tension gets strong enough, you get a saturation. So if you talk to a numerical person, Jim Stone, he's put Brzezinski MHD in his Athena code, and he gets something similar.
What's the difference in the ones that run up and the ones that don't?
Resolution. So the ones that don't capture these high K modes that feed off the pressure isotropy. I mean, that's what I'm guessing. We haven't talked about this yet, but
You're guessing that it was different resolution, or the reason the different resolution?
I'm guessing the reason. I know that they're different resolution.
Okay.
Yeah.
They're different lower resolution, right?
Yeah, they're lower resolution. Yeah. So these lines are at higher resolution, and they seem to capture these high K modes, and that deplete the pressure isotropy, and they let the MVI to continue to grow. And then
How high are the highest resolution runs he's doing here?
I think there was a 512 one actually. It's like
Really?
yeah.
What about the other two directions?
No, actually, no, you're right. It's a 256, 128, 128, I think. These other ones were like 32 and 64 in different directions. There hasn't, to my knowledge, because I haven't been in great contact with him, that I don't know how many of these he's run. So I don't know if this is a generic outcome of however he starts the simulations, but it seems sensible theoretically.
What's that second growth rate?
This thing, this is related to, well, I'm guessing, it's related to,
You must know in your model what that growth rate is.
yeah, yeah, and it works. I'm guessing it's when the MBI growth rate goes down and the mirror growth rate goes up and they become comparable. And this,
Then they just stay like that.
they just stay like that.
So last year I think we discussed this numerical reasons, right? Imagine that the secondary growth could be due to turbulent dynamic actions.
Right.
What's the velocity field associated with the MVI that you have produced? Does it look like turbulence?
Well, sorry, I didn't.
In the primary phase, you create also some velocity field, right?
Yeah.
So, and the question is, how can this velocity field drive turbulent dynamo, and what would be the growth rate associated with it?
Right. I don't know the answer to that question.
Is it obvious that the secondary mode is a mirror?
Well, we haven't seen inside James Bond,
Yeah.
right?
I haven't.
This thought is all we know.
I haven't seen any movies yet or anything. He told me that he doesn't see a marked contrast in once you get to this hump. So he doesn't see a huge contrast in the velocity field. That things, he says, still looks like MVI, just slower. But it's hard to say because these MVI, they're not channel solutions. You know, they're not like these beautiful MRI channel solutions where you could just look at it and you can see it.
No, but I'm not arguing that the velocity field has to change after that. I'm arguing that maybe the velocity field created during the primary phase then serves to amplify its magnetic field by turbulent dynamo.
Yeah, and this is a question he asked also. I don't know. All I know is that if you balance these two terms, the MVI and these secondary mirrors, you get something that looks an awful lot like the simulations. And so that's what I think is going on. But I haven't seen inside the box yet. So
These are really these are not small perturbations. So the issue with, I mean, the model might be a good model, but these are, you know,
This is-
D of
yeah.
1 10 to the 17.
yeah,
Right? So this is not linear growth of small perturbations on top of something.
right. And that's exactly why you can't formulate a rigorous nonlinear theory, because as soon as the pressure anisotropy becomes important, delta B over B is order unity, and then
You certainly have a nice exponential growth rate, it looks like, which you could compare to your theory, I would think, fairly clearly.
yeah, I've done that. It works out fine. Yeah, because he sent me one file.
But Jim's calculations, it's purely fluid
Right.
sound approach, just the Brzezinski viscosity.
Yes.
And that captures the physics of these. Embedded, or basically implicit in the Brzezinski viscosity, is this anisotropic pressure mirror instability.
Yeah. No, it's just. I mean, there should be a warning that it's very dangerous. You know, just like Greg Hammock cautioned, is there may be a fluid mirror. I can understand it from a fluid perspective, but there's also the kinetic mirror. And whether you actually do this in a kinetic calculation, which one wins out, I don't know. And this is the problem with Brzezinski simulations, and it's
Well, there must be parts of the box too where the field is going down.
right,
So there'll be fire hose in there.
right.
And the fire hose dispersion relation in Brzezinski is
It is the right one.
the real one,
Yeah.
and it goes. The fastest growing modes are at the box,
Right.
at the grid scale.
Mm-hmm.
Um,
Yeah, that's an issue. So we've been discussing this, whether to normalize them with gyroviscosity or not. The naive hope would be that the MVI is what's pumping your turbulence, and it's strongly preferring to generate a positive pressure isotropy. So you would hope that the volume filling factor of negative pressure isotropy isn't that much, because it's a net flux box. It's not a zero net flux box. In a zero net flux box, you would have just as much going up as going down and all sorts of stuff. But right, yeah, I'm sure there's negative pressure isotropies in the box somewhere. You have to have them in a turbulent field. So,
Well, on average, of course, the field is going up,
mhm.
going down some places,
Yeah.
especially once you get to steady state, because it'll be good. There's a nice little balance where it's amplifying a little bit over here and going down over there, and there's a sort of net balance.
Yeah.
But then you also have the cutoff problem with MV1 with ER. Because there's no cutoff.
Yeah. It's not as bad.
Cutoff, it's not as bad because it's not rising.
Yeah. I mean, it's as long as you put your grid zone somewhere beyond where it just flattens out, it doesn't matter where you put it, right? Because you'll get the same growth rate, but not for the fire hose, right? And this is a problem. Yeah. I don't know how to handle this. I mean, the one approach that Pratik took was to just limit the pressure isotropy from above and below within the box artificially, and
Well, I think what Pratik saw in his simulations, if I remember correctly the numerical results, was that they were actually very rarely sitting, at least on the average, they were very rarely sitting on the fire hose threshold.
well, that was integrated over the box.
But it looked like they were always trying to sit at the upper threshold rather than at the lower.
But that was integrated over the box.
But that
Yeah,
wasn't really.
yeah. That's the problem. Yeah.
Yeah, but so in some average sense, the fire hose was not a problem for them. I'm sure locally it was a problem.
I haven't talked to him
Well,
about
that might only be during the time that you've got dynamo action. Once you've got to steady state,
That's well, no, they didn't have dynamo action. They just had steady state simulation.
I
Well,
think
at least you know their plot of alpha looks like a.
There might have been a dynamo phase, but we were trying to run them long enough so that we were focusing on the steady state phase.
yeah.
Um,
There's also
and-
something that I think would be very valuable if Pratik did, would be to run the simulation starting from a higher beta. Because, I mean, this is unrealistic because there's all sorts of other physics that comes into this high beta. But, still.
Yeah, but it explores the sort of
Yeah.
limits of the regime. Right?
So that would be useful. Okay, so I'm out of time. I was just going to make a caution that when you're starting a simulation like this at a beta of 10 to the 17, you should really worry about FLR effects, gyroviscosity, and I'm putting that in now. You get a ton of terms. I'd be happy to talk with people, but maybe I should just stop here.